Alright, so in this video I'm going to show you how to use proof by induction to prove the Moivre theorem. Okay, and it's an expectation from the syllabus. They expect you to know how to use the proof by induction to prove the Moivre theorem. And there are a couple of prerequisites before we actually do the proof. For example, you need to know how to use the compound angle formula from trigonometry, which can be accessed from the information booklet. So what I mean by that, if you've never seen it, is the formula I'm going to write on the board right now. So they expect you to know the formula of cos A plus minus B and sine of A plus minus B. All right? So you're going to see that in the video I'm going to actually refer to the compound angle formula. So basically cos A plus B is cos A cos B minus sine A sine B. Alright, and all these formulas are actually given in the information booklet, so we're not going to spend too much time actually going through that formula. But just because I'm going to reference it in the proof, I'm just telling that to you right now. So I'm just going to erase that because the session is not on the compound angle formula but the Moivre theorem. Alright, so what we basically need to prove is the Moivre theorem. So I'm first going to actually write it down. So the Moivre theorem is used when we're actually taking a complex number to a given power. Alright, and you have its extension where the power is a rational number, and the formula is actually a bit different when you have the rational number, and you can actually go and watch the video where we actually try to find the square root or the cube root of a complex number, and we use the extended version of the formula. But this one is the basic Moivre theorem formula, whereby you have a complex number and you're taking it to a given power n. So what happens is that the modulus takes the power of n, and the argument of the complex number in polar form gets multiplied by n. So that's basically what the Moivre theorem is. Now we're going to apply the principles of proof by induction, which was developed by Al-Karaji to that formula. So step one is assuming, no, we're not going to write the assumption first. We're first going to test it like you usually do. However, as the first step of proof by induction was testing, can you really test it here? You can't really test it because it's a statement compared to the previous ones whereby you have a left hand side and a right hand side and you replace n by 1. So that used to be the first step of proof by induction, but over here we can actually start by replacing n by 1. So you get z1 equal to r cos theta plus I sine theta. So it's not really us really proving something by replacing n by 1 on the left hand side or the right hand side, but if you want to actually try n equal to 1 on both sides, you can do it, but it gives you a very different feeling, because in the other formula we proved we could actually quantitatively see what was happening on the left and what was happening on the right, but over here it's a statement, so it doesn't give you the same feeling or same feeling of satisfaction whereby you had a number on the left and a number on the right. So we're going to keep the first step, which is n equal to 1, but like I said, it has a different feeling to it. So we'll keep that as step 1. And then step 2 is the assumption itself. So in step 2, we are assuming that it's true for n equal to k. So we assume that for n equal to k, the statement is true. Okay, the statement is true. So what happens? If n is equal to k, then you get zk is equal to r power k, open brackets, cos k theta plus I sine k theta. So for n equal to k, this is what happened. Okay, this is the statement. And then we have to prove for n is equal to k plus 1, the statement is true. Okay, that's the third step. So you'll see that the steps stay the same as the previous ones. So when n is k plus 1, then you get z power k plus 1 on the left is equal to r to the power of k plus 1, open bracket, cos, you replace the n by k plus 1, so cos k plus 1 theta, plus I sine of k plus 1 theta. Okay, so this is the statement we have to get. And if you wish to actually expand that part, you can do that. So it can become cos of k theta plus theta plus I sine of k theta plus theta. Alright, so that's the zk plus 1 statement. And as with the other questions on proof by induction, we actually need to now prove that statement using our assumption, so using step 2. So we're working with zk plus 1. Now zk plus 1 can be broken into zk times z power 1 using indices. And then this gets written as rk, because the zk is that statement here, so I'm going to use the statement from step 2. So it's rk cos k theta plus I sine k theta multiplied by z1. Z1 is step 1 actually. So in this proof, you actually use step 1 and step 2, unlike the other proofs by induction we had. So it's r cos theta plus I sine theta. Alright, so that's the statement we have to work with. I'm going to continue on the right hand side. I'm going to draw a line here. So rk plus 1 stays here, and how are we getting rk plus 1? I'm just multiplying the rk to r power 1, so that combines into rk plus 1. Then what can I do? I can take this bracket and actually multiply to the other bracket. So I'm going to write it down here. So what's happening is rk is multiplied to r1, giving rk plus 1. Then you're going to actually multiply these two square brackets. So the cos k theta will multiply to the cos theta. The cos k theta will multiply to this one, I sine theta. Then the I sine k theta will multiply to this one, and the I sine k theta will multiply to the I sine theta. Alright? So this is what's going to happen in the multiplication. I'm going to write the statements here. So when cos k theta gets multiplied to cos theta, you get cos k theta cos theta. Alright? Then cos k theta gets multiplied to I sine theta, you get plus I. You could write the sine theta first if you want. So I sine theta cos k theta plus the I sine k theta gets multiplied to the cos. That gives you sine k theta cos theta I. Then the I sine k theta gets multiplied to the I sine theta. That one gives us I square sine k theta sine theta. So we end up getting that long statement after we multiply. Alright, and we try to simplify further. So it's rk plus 1, open bracket, cos k theta cos theta, plus, we have two terms having the I notation in it, so we can factorize the I out. So I, open bracket, cos k theta sine theta plus sine k theta cos theta, close bracket. And then over here, the I square can actually be replaced by -1, so that you get minus sine k theta sine theta. Okay, so we get, once again, the very long statement. All right, and with complex number, we usually group the real parts together and the imaginary parts together. So what I'm going to do is I'm going to actually group these two these two parts together because they don't have I with them. So I'm going to rewrite it by actually including the real parts together first. So it's cos k theta minus sine k theta sine theta plus the term with the I, which is I cos k theta sine theta plus sine k theta cos theta. All right, and cos k theta minus sine k theta sine theta. It's cos A cos B minus sine A sine B, which is just cos of A plus B. All right, referring to the compound angle formula. So that's as if A, that's B, that's A, that's B. So on your formula sheet, you'll see that if you have cos A cos B minus sine A sine B, it's cos of A plus B. All right, so this actually gets simplified to cos of k theta plus theta. All right, and plus I, and this statement is actually sine of k theta plus theta. All right, and this is exactly the statement we should have got if we just replaced in the Dumas theorem for k plus 1. So we've actually proved the Dumas theorem using mathematical induction, and you know the last step whereby we say that since it's true for n equal to k plus 1, therefore it's true for n equal to k, then it's true for all values of n. All right, so that was a proof by induction of the Dumas theorem. And for exams, you can actually be asked to prove the Dumas theorem for not just z power n, but z power 3 or z power 4, but the steps would remain the same. And in each proof by induction, when it comes to the Dumas theorem, you always have that compounding angle in it, and you have to refer to the compound angle formula. And to me, the catching point here is over here at this stage, whereby you really need to see that this expression comes from cos A plus B, and that other expression comes from sine A plus B. And your A is the first angle, k theta, and your B is the second angle. So to me, that's the most important part in that proof.